So as you've seen in the past few videos, although I need the things listed in the sample space as kind of an intermediate step for a lot of problems, what I'm really interested in the end is counts. And so there's going to be some ways that we're going to work through to actually figure out counts, like in other words, there are 8 possibilities when I flip 3 coins, so that I don't need to actually write out a whole sample space to do things. And one of the most common ways we kind of get around that is by looking at contingency tables. Now, these are going to be something that we use for what's called empirical probabilities versus theoretical. So theoretical probabilities are based off of being able to figure out everything that could possibly happen, and where everything's going to be equally likely, so we can just figure out exactly what the sample space looks like and what our events look like. Empirical probabilities are actually based off of what we've seen in real life. So they're kind of estimates of those true theoretical probabilities. But they're very easy to work with because realistically empirical probabilities are just proportions like we've done before. So a contingency table is basically this. It's a table of values, specifically of counts, like you've seen tables before, but where the rows are mutually exclusive and the columns are mutually exclusive. That way, any observation that we have only goes in one place. Now let me explain what mutually exclusive means real quick in case you don't know. It means that if 2 events are mutually exclusive, then one and only one of those events can occur. Heads and tails would be an example of mutually exclusive events. I could get heads, but if I do, it's not tails, right? So heads and tails are mutually exclusive events. Many things that we work with in specifically this classical probability stuff that we're doing are mutually exclusive events. Getting a 1 or a 3 when I roll a die is mutually exclusive. Now what about drawing a card from a deck of cards? Getting a black card and getting a heart, right? So are mutually exclusive because hearts are red, right? But getting a red card or a heart are different events, but they're not mutually exclusive because both of those can occur at the same time. So that's what mutually exclusive means. The fancy math word for it is disjoint because we're working with sets, but I don't really care about that. Mutually exclusive is what we usually say in plain English. So let me give you an example of a contingency table. So I've got this contingency table where I've got online and live students, and I've got freshmen and sophomores. So you can't be both a freshman and a sophomore at the same time. And you can't both be in my online or live class. You've only got one of those two, right? So this is a contingency table, and I've got counts in it, right? So this number 47 here means that I've got 47 students that are sophomores in my live, like face-to-face class. This 1 here means there's 1 freshman in my online class. So let's start to use this thing. So the first thing I want to do is find the row and column totals. That's going to really help me as I go through the calculations. So I'm going to pause the video and put that on my board so that I can use it. Just a second. Okay, so I've got the table now behind me. And when I find probabilities, it's always how much of the whole, right? It's always a proportion. So I need to find the whole, right? How many is there total? So let's find the totals here, right? So 1 plus 24 is 25. That means I had 25 total online students. This 2 and 47 gets me 49. That's how many live students I had. If I add 1 and 2, that's how many freshmen I had, which is 3. And 24 plus 47 is 71, which is how many sophomores I had. And then when I add up these two or these two, they'll get me the same number. I'll get 74 as the total number of observations I have. All right. So just to demonstrate the contingency table's usefulness here, I want to find a few probabilities. So first off, let's find the probability that the student is a freshman if I just randomly select one of these students. All right. So the probability that I have a student that's a freshman. All right. Well, how many students are freshmen? 3. Out of how many total students do I have to pick from? 74. And we're done. That's pretty easy. Now, this is a empirical probability. These are usually a lot easier to work with. But we're going to have a lot of these in this course to make your life not so miserable. So next, let's find the probability of getting a sophomore that studies online. So a sophomore and online, right? A sophomore that studies online is both a sophomore and online. So how many of these sophomores study online? There are 24 of them. And again, I'm just randomly picking one student, so it's out of 74. It's 24 out of 74. That's it. All right, now let's deal with this last probability I give here. If a student studies online, what's the probability that they're a sophomore? As you'll see a little bit later in this unit, this is a difficult probability to find if we don't have a contingency table, because we have to use something called conditional probability. So I'm not even going to write out how I write this probability, because we haven't gotten there yet. I just want to think about this intuitively. So if a student studies online, what's the probability they're a sophomore? Well, first off, I said if a student studies online. I'm only interested in my online students then. I'm only interested in these 25. Right? I'm not interested in my face-to-face. I said if a student studies online. So I'm only interested in these 25 here. All right. Well, that's how many total there are. I said, so if a student studies online, what's the probability they're a sophomore? Well, there's 24 sophomores out of these 25. I'm done. That's it. Okay. So these contingency tables are a lot easier to work with. We just kind of think it through, and we'll get lots of practice with that. But we just think it through with these contingency tables, and it's a lot easier than making tree diagrams and writing out sample spaces and all that stuff. Now, admittedly, it's going to give us an empirical probability instead of theoretical. In other words, it's going to be based off of our experience rather than truly what happens, right? Because maybe next semester I'll actually have different numbers here, and this will change. But that's okay. Generally, this empirical probability is just fine. It gets us the answers that we need.